Hello, learners. Welcome back to 5Rs, where we make physics simple, meaningful, and connected to real life and faith. Today, we'll explore the lens equation, an essential tool for understanding how lenses form images.
A lens is a transparent optical device that refracts light. There are two main types: convex or converging lenses, which bend light rays inward, and concave or diverging lenses, which spread light rays outward. Before we dive into the formula, let's define some key terms. Focal length, f, distance between the lens and its focus. Object distance, d, distance from the object to the lens. Image distance, di, distance from the image to the lens. Magnification, m, tells us how large or small the image is compared to the object.
The lens equation is written as 1 over focal length equals 1 over object distance plus 1 over image distance. Mathematically, it looks like this. 1 over f equals 1 over do plus 1 over di. Here, f stands for focal length, do is the object distance, and di is the image distance. This formula allows us to predict where an image will form when light passes through a lens. Another important idea is magnification, given by the formula m equals hi over ho equals minus di over do. The sign of magnification tells us about the orientation of the image. A positive m means the image is upright and virtual, while a negative m means the image is inverted and real. The size also depends on the absolute value of m. If the absolute value of m equals 1, the image is the same size as the object. If the absolute value of m is greater than 1, the image is enlarged, and if m is less than 1, the image is smaller. When working with the lens equation, always remember the sign convention. For focal length, a convex or converging lens has a positive focal length, while a concave or diverging lens has a negative focal length. For object distance, the object is usually placed on the same side as the incoming light, so the object distance is taken as positive. For image distance, if the image is real and forms on the opposite side of the object, it is positive. If the image is virtual and forms on the same side of the object, it is negative side as the object, it is negative. For heights, an upright image is taken as positive, while an inverted image is negative. A convex lens can create different types of images depending on the position of the object. If the object is placed beyond twice the focal length, beyond 2f, the image forms between f and 2f, and it is real, inverted, and smaller. If the object is placed exactly at twice the focal length, at 2f, the image is located at 2f on the opposite side, real, inverted, and the same size. If the object lies between f and 2f, the image is formed beyond 2f, and it is real, inverted, and enlarged. If the object is placed at the focal point, at f, no image is formed because the rays come out parallel and never meet. Finally, if the object is located inside the focal length, between the lens and f, the image is formed on the same side of the lens as the object, and it is virtual, upright, and magnified. A concave lens, on the other hand, always produces the same kind of image, no matter where the object is placed. It always gives a virtual, upright, and diminished image. This is why concave lenses are commonly used in eyeglasses for correcting nearsightedness. Let's solve our first example. Suppose we have a convex lens with a focal length of 10 centimeters, and the object is placed 30 centimeters away. Using the lens equation, 1 over f equals 1 over do plus 1 over di, we substitute the values to get 1 over 10 equals 1 over do plus 1 over d, I 130 plus 1 di. Solving for di gives us 15 centimeters. Now let's find magnification. M equals negative di over do equals negative 15 over 30 equals negative 0.5. The negative sign tells us the image is inverted, and since the magnitude is less than 1, the image is smaller. Sample problem 2. An object is placed between the focal length and twice the focal length. Suppose f equals 15 centimeters and DO equals 20 centimeters. What is the image distance and magnification? Substituting into the equation, 1/15 equals 1/20 plus 1 over di. Solving for di gives 60 centimeters. The magnification is m equals negative 60 over 20 equals negative 3. This means the image is real, inverted, and 3 times larger than the object. Sample problem 3. Let's place the object inside the focal length or between f and the lens. Suppose f equals 10 centimeters and do equals 6 centimeters. Substituting into the lens equation, 1 over 10 equals 1 over 6 plus 1 over d. Solving gives di equals negative 15 centimeters. The negative value indicates a virtual image on the same side as the object. The magnification is m equals negative 15 divided by 6 equals plus 2.5. This means the image is upright, virtual, and 2.5 times larger, just like when you use a magnifying glass. An object is placed 15 centimeters in front of a concave lens with a focal length of 10 centimeters. Since it is a diverging lens, the focal length is taken as negative, so f equals negative 10 centimeters and DO equals plus 15 centimeters. Using the lens equation, we substitute the values, then simplify, we get di equals negative 6 centimeters. A negative value for the image distance means the image is virtual and located on the same side of the lens as the object. Next, we calculate the magnification using the formula m equals negative di over do. Substituting, we get m equals plus 0.4. A positive sign tells us the image is upright, while a value less than 1 means the image is smaller than the object. Therefore, the concave lens produces a virtual, upright, and diminished. Lenses are everywhere in daily life. Convex lenses are used in cameras, projectors, microscopes, and magnifying glasses. Concave lenses are used in eyeglasses to correct nearsightedness and in peepholes on doors. Understanding the lens equation helps us appreciate how these devices work. Just like a lens takes scattered light and focuses it into a clear image, God helps us focus our lives when everything feels scattered. Sometimes our problems look magnified, but God is always greater. At other times, we may feel small or diminished, but in God's eyes we are always in focus. The Bible reminds us in Psalm 119, verse 105, "Your word is a lamp to my feet and a light to my path." Thank you for learning with 5 R's. Don't forget to like, share, and subscribe for more exciting physics lessons. Until next time, keep exploring and stay curious.